Hi everyone, I hope you're okay, and I hope that the videos we keep uploading are helping you out. This is the 10th video, guys, which simply means I'm doing the 10th question, whereby I'm answering past exam question papers, but I'm only focusing on Doppler effects. Answering exam-like questions, guys, it's very important for you because it will give you an edge whenever you write your exams. I believe that if you share the video to your peers, they will also have that edge. Uh, Writing exams will become more comfortable and easy for them. So please do watch the video, guys, and obviously watch the other videos because I do this series for each and every topic. Uh, for now, we are dealing with Doppler effects. Watch all the 11 videos of Doppler effects where I'm tackling past question papers. But if you still want to learn Doppler effects is just a short chapter. Um, I will put the link there on the description, whereby you can click that link, watch the video, learn Doppler effects, and then you're okay. For now, yeah, let's just answer this one. Yeah? Okay. We are told that a car moves at a constant speed at 10 meters per second towards a stationary source. Are you together? And then the sound source the sound source emits sound waves of 880 hertz. A sound detector A is attached to a car, and another sound detector B is attached to the sound source. Okay. The detector B rather detects sound waves reflected from the car. The speed of the speed of sound in air is 340 meters per second. What happens over here, guys? We'll simply consider first the motion between, rather the relative motion between the car and the source. All together, the source emits the frequency of 880 hertz. All together, which simply means that the listener in the car will detect a frequency which is higher than 880 hertz. Why? Because the car is moving towards a stationary source. Are you together? And then for the next one, the reflected frequency of the source, ne? The reflected frequency, that means UB will reflect a greater frequency than that which was detected by UA. Now, now these things changes. A will become the source and then B will become the listener. Since A is moving towards B, it simply means that B will detect a higher frequency compared to that of A. Please do not mix these two scenarios. They are two different things. Are we together? These two scenarios are two different things. You have one scenario and the second scenario there. Okay. Now let's answer these questions. Firstly, they want us to state Doppler effect in words. It simply states that Doppler effect is just the apparent change in the observed frequency of the source as a result of relative motion between the observer and the source. And then 6.2, they want us to calculate the wavelength of the sound waves emitted by the source. I know that frequency multiplied by wavelength is equal to the speed of sound in air. My frequency is 880 hertz. The wavelength is what I do not know, but I know that the speed of sound is 340. So my wavelength is simply 340 divided by 880. Excuse me. 340 divided by 880. We will simply get 0.39 meters. 0.386, that's basically 0.39 meters. Okay, so the wavelength is 0.39 meters. Calculate the frequency of the sound waves detected by A. we are still focusing on the first scenario. Are we together? For my first scenario, the frequency detected, that's what I'm looking for. The frequency of my source is 880 hertz. The velocity of my listener is 10 meters per second. The velocity of the source is stationary. The speed of sound is given as 340 meters per second. So for me to find the frequency detected, I just need to substitute. I have my formula. It says FL is equals to V plus minus the velocity of the listener, and then V plus minus the velocity of the source, all multiplied by the frequency of the source. Remember that, guys, my source is stationary. So my numerator, I'll only have the speed of sound, which is V. Né? Why? Because Vs is equals to 0. So at the top, I will have V, and I'll also have velocity of the listener multiplied by the frequency of the source. But now, guys, please note that whenever the listener is moving towards the stationary source, our numerator will have a positive there. So we'll just substitute. We'll simply have 340 plus 10 all over 340, all multiplied by 880. I'm expecting to find a frequency which is higher than 880. Why? Because the listener is moving towards the stationary source. That's 340 plus 10 divided by 340 multiplied by 880. This will give me 905.88 hertz. 905.88 hertz. Are you together? So this will detect a sound, a frequency of 905.88 hertz. Okay, then now we are told that the sketch below shows the frequency recorded by detector A. That's the frequency recorded by detector A, and the frequency we got 905.88 hertz. Are you together? And then we are being asked to redraw the graph, the graph above for detector A in the answer book. And on the same set of axes, we must sketch the graph of the frequency recorded by detector B. Label the graph as B. Please note that, guys, since now we are talking about the reflected frequency, which simply means A will become the source and B will become the listener. Are you together? Which simply means that the frequency detected by B must be greater than that of A. Why? Because A is moving towards B. So my frequency will just be like this, and then I'll just have B over there. That's the only thing I was supposed to do. Yeah, so just stay tuned, guys, and that's how you're supposed to tackle this Doppler effect. Yeah, just wait for more videos.